Hello, everyone. Last week, we briefly mentioned the fundamental theorem of calculus, and we're just formally going to go through the statement now and just discuss quickly what it means. And then we'll apply it by doing area between curves, and then we'll do substitution method. So recall from last week that we defined an indefinite integral of a function to be its antiderivative. And then we defined a definite integral of a function to be a limit with respect to the Riemann sum. And we thought about this as being area underneath the curve, in particular from the curve underneath the x-axis or vice versa. And here we're going to examine these two concepts together using the fundamental theorem of calculus. And yes, it's very fundamental. It's technically in two parts, but here we kind of state it in one. And what the statement says is that if we have some sort of continuous function on some interval AB, sometimes it's just stated as a continuous function, but we're going to say on the interval. Then if we consider the integral of this continuous function going between, say, the point A and x, where x is a variable, so it's not a point for an upper bound. And we write the actual integrand as f of t dt. So yes, these variables are different from what you see here. And the reason why we write it like that is we refer to this as the antiderivative, capital F of x. And the reason why it's written like that is because when we think about now differentiating this expression, so capital F prime of x, or df dx like this here, then we're thinking about taking d dx of our integral. So the integral going from a to x, f of t dt. And the reason why it's written this way is because if we were to actually evaluate this, we would have our antiderivative at x, so capital F of x, minus the antiderivative at a. So when we differentiate that, the part with the constant would go away, and we would be left with little f of x. Okay, so the notation may look a little bit weird, but the punchline behind this part of the theorem basically says to us that integration and differentiation, they're inverses of each other. So if we differentiate an integral, we almost think about them as canceling out. Or if we have a derivative and then integrate, again, we think about it like canceling it out. So that's the punchline of this first statement. And then the second statement we actually already gave, it tells us how to evaluate an actual integral. So we would find its antiderivative, capital F of x, and then we would first evaluate it at the top bound or limit of integration, b, and then we would subtract it from the lower limit or bound of integration. Okay, so the first part tells us that integration is the reverse of differentiation. And then we also know how to solve an integral by evaluating its antiderivative between the bounds a to b. And then as another remark, the integral of a continuous function allows us to find the total change of a quantity, assuming that the actual integrand represents a rate of change. And that was something that we also mentioned last week. Okay. There's also another interpretation or another application, I guess, to integrals. So we said before that the integral can represent the total change of a certain quantity if the integrand represents the rate of change of something. But let's say that we're given some sort of data set. And the example I'd like to use is, say you're given, temperature outside throughout the day. Say every hour you take a temperature reading. You can also use integrals to let you find the average value of the temperature during a day. Or in general, if you set up the integral a certain way, you can basically look at an average value of some sort of quantity. And this is a definition. So say we have a continuous function over AB. Then the average value, okay, and we'll just call it F and then subscript AVG. over a to b is given by, so we'll have our integral going from a to b, f of x dx. But then to see the average of something over that interval, we multiply our integral by 1 over b minus a. Okay, and let's just do an example so you can see how it works. So this is the average value of some sort of quantity over an interval. We find that by taking the integral and then multiplying it by 1 minus b over a. So let's say we're doing an example where we talk about engine emissions. So let's say that the emission of an engine is given by this expression here. E of t is equal to 2t squared, where E of t itself is the engine's rate of emission in billions of pollution particulates per year at time t, where t is in years. We want to find the average emission from the first year to the 5th year. So for something like this, we're just going to use this definition. We look at the integral going between certain bounds. So for us, our a would be 1 and our b would be equal to 5. And then we're going to plug in this expression here for the engine's rate of emissions, so 2t squared. And then we'll multiply the whole thing by 1 divided by 5 minus 1. Okay, so we're going to get here 1 divided by 5 minus 1. And then we're going to integrate between 1 and 5. Our integrand is going to be 2t squared, and we are integrating with respect to t. Okay, so the constant out front, we're going to get 1 over 4. The antiderivative of our integrand, I'm going to leave the 2 out front here for a second. And then by reverse power rule, I'm going to get t cubed multiplied by 1 over 3 out front. And we don't put plus c because this is a definite integral, so we need to evaluate it between 5 and 1. Okay, so let's just simplify this first a little bit. All these constants out front. So this 2 can cancel with the 2 at the bottom. So we would get 1 over 2 times 1 over 3. So that's going to be 1/6. And then, so I'm factoring out this part outside of where I'm going to evaluate t. And then I'm left with t cubed. I want to evaluate that at 5. So I have 5 cubed minus 1 cubed. And then I'm going to get, 1 over 6, 125 minus 1. So I'm going to get 124 over 6. And if you simplify that a little bit, you can get 62 over 3. And remember what this represents, billion pollution particles or particulates per year. Okay, so integrals can be used to find area underneath a curve. They can physically represent the total change of a quantity. And if you adjust it slightly, they can also represent an average value of a quantity over a certain interval. Okay, thank you very much.